Okay, let's start the class. So in last class we have studied the AC voltage controller of bidirectional type. So today you can see the small derivation for the RMS voltage, RMS current and the power factor for that voltage controllers. So before that you are aware of that the CO4 internal exam will be starting from 23rd November. So our exam Power Electronics will be starting from will be on 24th November, Tuesday. So I think all the students have installed safe exam browsers, and we have conducted mock tests for the practice of that exams. So I think you have been practiced, right? And you are also aware of the question pattern, right? 10 MCQ questions of each of 1 marks and two 10-mark questions. So you have to write and scan it and upload that PDF. So it will be of 1 hour test, I think, 2 to 3, and 15 minutes extra time will be given for uploading the PDF answers, right? So please be prepared for that. So CO4 and CO5 will be conducted individually or separately, and you have to attend that both of the exams, and that will be considered as the internal exam for that concerned COs, right? So apart from that, we will be you have posted some indirect assessment questions, that is MCQ. So take care of that, and you have to carry out that MCQs before that exams, right? So now we can start. So last class we have seen this bidirectional AC voltage controller for the resistive loads. So this is the circuit diagram. It will be having two anti-parallel connection of thyristors T1 and T2. T1 will be conducting for the positive half cycle, and T2 will be conducting for the negative half cycle. So T1, the conduction period will be from 0 to pi, but we can delay the firing angle from 0 to pi, so that we can vary the output voltage. So here the alpha is your firing angle, so it can be varied from anywhere from the 0 to pi. And for similarly for the T2 thyristor, the firing angle can be varied from pi to 2 pi. Depending upon that, the output voltage can be varied, right? So if alpha is equal to 0, so the maximum voltage will be obtained. And if alpha is equal to 180 degree, the output voltage will be 0. So the alpha should be symmetrical for the T1 and T2. Suppose if we are taking the alpha as 30 degree, means the triggering angle or the firing angle for the thyristor T2 should be pi plus 30 degree, that is 180 plus 30, that will be 220 degrees. So the firing angle should be symmetrical. So if alpha is equal to 30 degree or 60 degree, means so that should be added with pi for the T2. And for the resistive load, the voltage and the output voltage and output current are symmetrical, since the both will be in phase. So both will have the same waveform nature, but the magnitude alone will be different. So V naught, the output voltage, will have the magnitude of the input voltage Vm, and the output current will have the maximum value of V naught divided by Vm divided by the resistance value Vm divided by R. And both the I naught and IS, I naught will be your output current and IS will be the source current. So both will be same. Since whenever the thyristor will be in on condition, you will be getting the output current. So at that time only we are drawing the current from the source. So the output current and output the source current will be same. So I naught and IS will be same, but we can see the V naught and Vs are different. Vs will be the source voltage and V naught is the output voltage. Both will have different waveforms, but the I naught and Is will be the same waveforms. That is your output current and the supply current are the source current. And the last two waveforms are the thyristor voltages, voltage across thyristor 1 and voltage across thyristor 2. So this thing I have already explained in the last class. Now we can go for the directly for the derivation. So this is your V naught, that is RMS value of the output voltage V naught R. So this is your half wave symmetrical waveform. So what is going to be half wave symmetrical waveform? So it will be same. That is a positive half cycle will be the same, and it is a reflector or negative and positive half cycle will be of same waveform nature, so that we can say it as half wave symmetrical waveform. So if it is an half wave symmetrical waveform means we can take the total period as for a half cycle. So here we have taken the period as pi. So this is the time period for the half cycle. So we are taking it as half cycle means since it is an half wave symmetrical waveform, and the waveform nature will be Vm sin omega t. That is your supply voltage Vs will be equal to Vm sin omega t. So that we have taken it as Vm sin omega t, and the omega t will be varying from alpha to pi. So alpha is your firing angle, and the output voltage we are getting from 0 to alpha, the output voltage will be 0, the V naught is equal to 0, and alpha to pi only we are getting the output voltage. After giving the firing angle only we are getting the output voltage, so that will be in the nature of Vm sin omega t. So from 0 to alpha the output voltage V naught will be 0, and alpha to pi we will be getting Vm sin omega t as the output. So here for calculating the RMS voltage, we are squaring it and we are taking the square root. So the limit will be alpha to pi and Vm square, Vm sin omega t. So it should be taken square, and we have to take the square root. So Vm square sin square omega t d omega t, right? So in this we have to integrate the sin square omega t. So we can take the Vm square outside, and sin square can be written as 1 minus cos 2 omega t by 2, right? So 1 minus cos 2 omega t by 2. The sin square omega t can be written as 1 minus cos 2 omega t by 2, and the expression will becomes 1 by pi, and the 2 can be taken outside, and Vm square also can be taken outside the limit since it is a constant, and the remaining things will be 1 minus cos 2 omega t to the limit of alpha to pi d omega t, right? So to the whole power of 1 by 2, and we have to integrate this. So the remaining terms will be same, and if you are integrating the 1 means we will be getting omega t minus cos 2 omega t will be of sin 2 omega t by 2. If we integrate cos 2 omega t means we will be getting sin 2 omega t by 2 to the limit of alpha to pi. The remaining terms, the Vm square sin by 2 pi will be same, and the whole power of 1 by 2 will be as it is, and we have to substitute the limit. It is pi minus alpha minus sin 2 pi divided by 2 minus of minus plus sin 2 alpha divided by 2. Here we will be having the Vm square divided by 2 pi, and the whole power of 1 by 2. So in this term will be gets cancelled since sin 2 pi will be 0. So this term will vanishes, and the remaining term will be pi minus alpha plus sin 2 alpha by 2. So out of this bracket we will be having Vm square by 2 pi. So in this we can take this Vm square by 2 outside this square root, so that we will be getting Vm by root 2, and here we will be having 1 by pi into pi minus alpha plus sin 2 alpha by 2 to the power of 1 by 2, right? So this is your expression for the RMS output voltage and the RMS output current. I naught R is the RMS output current. So that will be equal to RMS voltage divided by the resistance. Since we are having the resistive load, so it is divided by R, and this is your power delivered to the load. So the capital P is equal to power delivered to the load. So that can be I naught R square into R, or V naught R square divided by R. So another thing, the maximum power will be delivered when alpha is equal to 0. So if we substitute alpha is equal to 0 means we will be getting the same as your input voltage. So here, this is your input voltage. So the positive half cycle is 0 to pi and negative half cycle is pi to 2 pi. So if we trigger the thyristor T1 at an angle of 0, so we will be getting the output waveform from 0 to pi, so that it will be the same waveform of Vs. And if we trigger the T2 at an angle of pi, the same output voltage and input voltage waveform will be same. So if alpha is equal to 0 means we will get a continuous sine waveform of maximum voltage. So if it is maximum voltage means the current will also be maximum. So if both the voltage and current are maximum means the output power, that is power delivered to the load, will be maximum. So the maximum power delivered will be load to, sorry, the maximum power will be delivered to the load when alpha is 0. Right. So next thing we have to calculate the power factor. So power factor, we will be knowing the formula. There is a basic formula: real power divided by apparent power. So the real power delivered to load will be V naught R square divided by R, and the apparent power delivered to the load will be equal to Vs into Is, or Vs into I naught R. Since I naught R and Is will be same, so Vs into I naught R, and I naught R is the RMS output current. So in previous slide, I have derived that expression, that is I naught R is equal to V naught R divided by R, and we can substitute both these equations in the power factor, that is real power divided by apparent power, that is V naught R square divided by R divided by Vs into V naught R by R. So here the resistance R will get cancelled. Then next one, here also we will be having the square, this square and the V naught R will get cancelled. So the power factor expression will be V naught R divided by Vs. V naught R is the RMS value of output voltage and Vs is the supply voltage, the RMS value of supply voltage. So this is the RMS value of the output voltage and this is the RMS value of supply voltage. So Vs will be the RMS value, so that can be written as Vm divided by root 2. So Vm is the maximum value of supply voltage. So in this waveform, so this is your Vm, and from this we can calculate the RMS value of Vs will be equal to Vm divided by root 2, right? So next thing, already we have derived the V naught R, that is RMS value of output voltage, as Vm by root 2 into 1 by pi minus alpha plus sine 2 alpha by 2 to the whole power of 1 by 2. So we can substitute this over here. Instead of V naught R, we can substitute this. Since power factor is equal to V naught R divided by Vs. So this Vm by root 2, we can write it as Vs. So this Vs and in the denominator we are having another Vs, both will get cancelled. So the net power factor will be is equal to 1 by pi minus alpha plus sine 2 alpha by 2 to the power of 1 by 2. So this is the power factor for the bidirectional AC voltage controller. So these expressions will be useful for your problem solving the problems, right? And the next thing, we can go for the integral cycle control. So already I have told there are two types of the AC voltage controllers. One will be phase angle control and another one will be integral cycle control. In a phase angle control, by varying the alpha, we are controlling the output voltage. That is, we are varying the AC output voltage by means of varying the firing angle. So that is called phase angle control. And in integral cycle control, we are turning on and turning off the source for few number of cycles, and we are turning off the source for the another few number of cycles. By turning on and turning off the voltage controller, we are controlling the output voltage. So that is called integral cycle control. So for integer number of cycles, we are turning on the voltage controller, and another integral number of cycles we are turning off the voltage controllers, so that it is called as integral cycle control. So this is the waveform. So Vs is your supply voltage or the source voltage, and here we are having the continuous sine waveform as your input voltage. And after this, so the last waveform will be your V naught, that is output voltage. So here we are turning on for few number of cycles. So here we can see the N is the number of turn on cycles and M is the number of turn off cycles. So you can see over here for the 3 cycles, the AC voltage controller is turned on. So correspondingly, we are giving the gate pulses. So the circuit diagram will be same. So already we are having the circuit diagram in the previous case. So this is your circuit diagram. So the circuit will be same, but the turn on method will be different for the phase angle control and the integral cycle control, right? So here also the T1 will be conducting for the positive half cycle and T2 will be conducting for the negative half cycle. And here we can see for positive half cycle of the source voltage, the triggering gate pulses will be given for the IG1, that is for the T1 thyristor. And for every positive half cycle, we are giving the pulses for the T1 thyristor. And for every negative half cycle, we are applying gate pulses for the thyristor T2. So here, for the total number of cycles, so the total period will be one half on period and one half period. That is plus 3 plus 2. 5 cycles will be the total time period. So out of 5 total cycles, we are turning on the AC voltage controllers for 3 cycles turn on and 2 cycles turn off. So N will be equal to 3 and M will be equal to 2. So out of 5 cycles, we are turning on the AC voltage controllers for 3 cycles and turning off the voltage controller for another 2 cycles. So similarly, it will be repeated for the further cycles. Another 3 cycles it will be turned on, another 2 cycles it will be turned off. So these type of integral cycle controllers are used for high thermal constant loads, since the high thermal constant load or high mechanical constant loads will not sense the turn off in between the cycles. So each cycles will be of 20 milliseconds, and here we are turning off the devices for 20 plus 20, that is 40 milliseconds. So the 40 milliseconds will not be sensed by the high mechanical constant loads or high thermal constant loads. So here 3 cycles it is turned on and 2 cycles it will be turned off, and depending upon the turn on cycles and turn off cycles, the output voltage magnitude will be varied. So if the number of on cycles will be high, means the output voltage will be high, and if number of off cycles will be high, means the output voltage will be low. So depending upon the number of turn on cycles, the magnitude will be high. And yeah, on another advantage of this integral cycle control will be, when compared to the phase angle control, the harmonics introduced in the output voltage will be less. Since we are obtaining pure sine waveform as your output voltage, the harmonics introduced in the output voltage will be less. So this will be preferred when we are going for the motor applications, speed control of motor applications. The harmonics introduced in the output voltage will be less, so that we can go for the motor control applications using this integral cycle control. So this thing is explained over here. It is another also called as on-off control, burst firing, zero voltage switching, and cycle selection or cycle syncopation. And the load is connected to source for some on cycles, that is N cycle. It is connected to load and it is disconnected from the there is a load is disconnected from the source for another cycles, that is M number of cycles it will be disconnected, and what is the merit will be less harmonics in the output voltage. And for this also we have to derive the V naught, there is RMS value of output voltage. So this thing we have to derive for each cycle. So we'll be having total time period as 5 cycles over here. That is M plus N will be the total time period. So M plus N will be the total time period, that is on cycle plus off cycle. So for this time period, we have to calculate the RMS output voltage, and out of that m plus n cycle, the AC voltage controller is turned on for only the on cycle, that is n. So the time period will be n by m plus n. So already we have seen in the chopper, that is T on divided by T on plus T. That is T on by T on plus T off. So likewise, the on cycle divided by on cycle plus off cycle. So this will be your time period. So here it will be represented as k, small k. So k is equal to, similarly in case of chopper, it is called as duty cycle. So here it is called as k, that is an factor that is equal to n by m plus n. So we have to derive, that is 1 by periodicity. So this is for the first cycle. So first cycle will be getting the full waveform, full sine waveform. So that is for 0 to 2 pi Vm square sine square omega t for the first cycle, and similarly for the second cycle, and similarly for third cycle. So it will be a full cycle from 0 to 2 pi. 0 to pi positive half cycle, and 0 to pi to 2 pi negative half cycle. So for each cycle, we will be having 0 to 2 pi of nature, that is sine waveform, Vm square sine square omega t. Since it is an RMS value, we have to take the the square, and we have to take the square root outside the whole V naught RMS. So here we have to take the square root, and V naught R is equal to the periodicity. Already I have told, that is for total n plus m cycles. The AC voltage controller is turned on for n cycle. So this will be your periodicity for total AC voltage controller, and for a single cycle, the time period will be 1 by 2 pi. So this 1 by 2 pi will be for single cycle, and the total number of cycles will be n plus m. Out of that, n will be for n cycles, the AC voltage controller is turned on. So that periodicity will be n by 2 pi into n plus m into 0 to 2 pi Vm square sine square omega t d omega t. So in this, the Vm square is taken outside, since it can be considered as constant, and the sine square omega t, already I have told in the previous derivation, that can be written as 1 minus cos 2 omega t by 2, right? So this 2 can be taken outside, so it will be 4 pi. So n into Vm square divided by 4 pi into n plus m into 1 minus cos 2 omega t. So here we have to integrate 1 minus cos 2 omega t with respect to the limit of 0 to 2 pi. So the same derivation, that is omega t minus sine 2 omega t by 2. So to the limit of, here the limit will be differing, that is 0 to 2 pi. So the upper limit is 2 pi and the lower limit is 0. So the sine term will be gets vanished. So for all zeros and in multiples of pi, that is the sine 2 pi at 3 pi 4 pi, all the terms will be 0. So this sine term will be vanished, right? So here sin omega t will be pi 2 pi minus 0, and this term will be automatically vanishes 0. So the V naught or the output voltage will be Vm divided by 4 pi into n plus m into n into 2 pi to the power of 1 by 2, right? So here 2 pi to the power of 1 by 2, so it will be root 2 into root pi, and already we will be having root of n by n plus m into Vm square divided by Vm square, it will be Vm, and 4 pi will be gets converted into, when we take outside the square root, it will be 2 into root pi. So this root pi, and here the another root pi will gets cancelled, and here we will be having root 2, and in denominator we will be having 2. So this 2 can be written as root 2 into root 2. So this root 2 will be gets cancelled, and in denominator will be having another root 2. So the net expression, the final expression will be Vm divided by root 2 into root of n by n plus m. So already I have told the n by n plus m will be k. So it can be written as root of k, and Vm by root 2 is nothing but your source voltage RMS value. The RMS value of source voltage will be Vm by root 2. So that will be equal, that can be written as Vs into root of k. Right? So Vm is the RMS value of source voltage. So that is nothing but your Vm divided by root 2, and k is equal to n by n plus m. It is the duty cycle of AC voltage controllers. And here also the RMS value of output current, the same formula, that is RMS value of RMS output voltage divided by the resistance. And here we have to calculate the input power factor using that same formula used in the phase angle control. And here also the power delivered to load will be V naught R square by R. So V naught R square we have already derived in the previous slide as V naught R is equal to Vs into root of K. So V naught R is equal to Vs into root of K, where K is equal to n by n plus m. So here we have substituted as Vs square, that is V naught R square is equal to Vs into root of K, that is Vs square into the roots gets cancelled since it is square, that is K is equal to n by n plus m. So it can be written as K into Vs square by R. And RMS value of input current will be equal to RMS value of the output current. So both the RMS input and output current will be same, and the input VA, that is your apparent power, will be equal to Vs into RMS value of source current. So Vs into Is, and Is and I naught are same, and I naught R is equal to V naught R divided by R, and input VA into power factor will be equal to power delivered to load. So from this we can calculate the input power factor is equal to power delivered to load divided by the input VA. So here the input power factor we can calculate the load, that is power delivered to load divided by input VA. So power delivered to load, we are having the formula as V naught R square by R, and input VA will be having the formula as Vs into V naught R divided by R. So if we substitute both these values, that is V naught R square divided by R divided by V naught R divided by R into Vs. So this term will be coming like this. So in this the R will get cancelled and V naught square will get cancelled. Finally we will get V naught R divided by Vs. So V naught R divided by Vs means, so here from this formula we can calculate this Vs can be go this side. So V naught R divided by Vs equal to root of K. So root of n by n plus m will be the input power factor for this integral cycle control. Then finally we can derive the average value of the resistor current. So here we have to substitute in terms of current. We are calculating, or we are deriving the current that is flowing in the each thyristor or any of the thyristor. So you can see this expression, that is you can see the waveform. So in this, the for one cycle the time period will be 2 pi. So out of this one cycle, the each thyristor will be conducting for 0 to pi. For a period of 0 to pi, T1 will be conducting, and the T2 will be conducting for pi to 2 pi. So for a full cycle, each thyristor will be having a conduction period of 0 to pi. So we can substitute the time period will be 1 by 2 pi, that is a full time period, that is periodicity will be 2 pi. So in that, the thyristor will be conducting for 0 to 2 pi, 0 to pi for first on cycle, and in second on cycle, that is another for 2 pi, we will be having 0 to pi, another second thyristor will be conducting. So on consolidating this, we will have the expression as for n plus n number of cycles, that is total cycles, it will be turned on for n cycle. So this is the time period for the total voltage controller. So in that, for single cycle, the time period will be 2 pi, and the limit alone will be differing, that is 0 to pi. For calculating the voltage, we will be having 0 to 2 pi as the limit. For calculating this average value of thyristor current, we will be having the limit as 0 to pi. So since out of a single cycle, each thyristor will be conducting for pi radians. So the limit will be differing, that is 0 to pi, it will be the limit, and the main things will be the same. That is the output current, sorry, the thyristor current will be Im sin omega t. So Im sin omega t is your output current. It is, the current will be the same nature. So this will be your Im and Im sin omega t. So we have to integrate. So Im can be taken outside, and integrating this sin omega t will be minus cos omega t, and we can substitute the limit as 0 to pi. So minus cos pi minus of minus plus, so cos 0. So cos pi will be minus 1, and cos 0 will be 1. So 1 plus 1, that is minus into minus plus, that will be 2. So we will be having this term as 0, sorry, 2. So this 2 and this 2 will get cancelled, and we will be having Im in here. So n into Im by pi into m plus n. So this n by n plus m can be written as k. So k into Im by pi will be the average value of the thyristor current. Similarly, we can calculate for RMS value of thyristor current. So what is the difference between all remaining things all same? So we have to take the square and we have to take the square root. So here also we have to derive the expression, that is we have to integrate the sin square omega t. So already we have explained in both the slides. So sin square omega t can be written as 1 minus cos 2 omega t by 2. So finally we will be getting the expression for the RMS value of thyristor wave current. So this is the RMS value of thyristor current. So the final expression will be Im into root of k divided by 2. Right. So after this, we can finish this class, and in next class we can see the ISC voltage controller for the RL. Right. So please be prepared for your exams and write well, so that you can, if you are missing the internal marks in the first exam or in first three CO streams, so you can gain the marks in this 4 and 5, so that you can boost your internal marks, and the final exam will also be in the online mode, so that you can practice this online exams in safe exam browser modes. Thank you.